So next lot of acute responses are to do with the cardiovascular system. So all of these, again, are working towards getting more oxygen to those muscles, because to create energy, we need oxygen, aerobically, that is. So how does our heart do that? One, our heart gets a bigger stroke volume. And stroke volume is how much volume of blood can we pump out with every beat. And another factor that increases is our heart rate, so how many times our heart increases. Now, the product of how much blood we're pumping multiplied by how many times our heart is pumping is called our cardiac output, and that is measured in litres per minute. So cardiac output is the volume of blood pumped out at the left ventricle with each beat, and we multiply that by how many times our heart rate beats. So what's interesting about cardiac output is that it doesn't matter whether you've got a trained or an untrained person, at rest the cardiac output is the same, because the oxygen demands of those two individuals is the same. This graph shows us how stroke volume reaches a plateau. It reaches its maximal at an intensity that is submaximal. So at rest, our stroke volume is pumping out approximately 60 to 80 mils per beat. Then when we start exercising, it gets bigger. It pumps more blood, and it will pump more blood until it gets to a submaximal intensity, and then the stroke volume, the heart can't get any bigger. It can't keep getting bigger and pumping more blood with each beat. So it reaches its maximal at a submaximal intensity. And that's why the graph is leveled off, because it is not a linear relationship, unlike heart rate. Heart rate has what we call a linear relationship with intensity. That is, as intensity increases, so does heart rate. It's a linear relationship. However, stroke volume, it increases, but then when we get to a submaximal intensity, it just levels off. It can't get any bigger. So how does the body get more blood around the body? Well, the heart rate, if I do heart rate in a different colour, heart rate, oh, that doesn't work, sorry. Heart rate will just keep going. So that's the way the body delivers more oxygen and more blood, not by the heart getting any bigger, it can't, but it just beats more quickly to get more blood around the body. Okay, blood pressure goes up. Only the systolic. You have systolic and diastolic. An average blood pressure reading is 120/80. The only time the diastolic, the lower number, would increase is if somebody is doing weight resistance exercise. And that's because all the muscles are tensing. It puts more pressure on the blood going back into the heart, because that's the measure of the diastolic blood pressure. Venous return to the heart. That is blood returning to the heart. So venous return is the body pumping blood back to the heart to remove waste. And how does it do that? Primarily through the muscle pump. By moving, that helps the veins push the blood back up against gravity back to the heart. And another way that the body does that, another mechanism, is through venoconstriction. So by constricting the blood vessels, that helps to push the blood up. Blood volume, as we said before, goes down. because within our blood, we've got red blood cells and we have plasma. So this is a test tube full of blood. If we were to spin it, we get our heavy red blood cells down the bottom, and this part of the blood is made up of plasma, which is made up of water, nutrients, salts. When we exercise, cellular respiration, a byproduct is water. When we exercise, we sweat, we lose water, and also we lose some salts in the blood as well. So therefore, our blood volume, is reduced due to the decrease in plasma, the plasma part of the blood. So that goes down. Next one, redistribution of blood flow. As you can see on the graph down the bottom shows you the percentage of blood between rest and exercise. So at rest, our blood goes from our heart, this is our heart, blood travels to our brain, about 22% goes to our kidney, about 20-something% to our liver, about 20% to our muscle. It's delivering the appropriate amount of oxygen for those organs and tissues to do their job. However, during exercise, our muscles, we are demanding oxygen. We need oxygen for cellular respiration. Oxygen plus glucose gives us energy, carbon dioxide and water. We need lots of oxygen. So where do we get it from? What our body does is our body constricts, called vasoconstriction and vasodilation. So what that means is that we have a narrowing of our arteries, and they're getting smaller. So what happens? If you've got a hose and if you've got a tap, our heart is the tap, and if you put a smaller hose onto the tap, you're going to have less water coming out. So this is reduced to about 4%, to about 5%, to about 7%. There's not as much blood travelling through there due to vasoconstriction. Now conversely, to get our muscles during exercise up to about 84%, how do we get that? We've turned off all these taps or tightened them. What do we do with this one? We increase it. That's called vasodilation, which is the opening up of the blood vessels. This is called vasodilate. So that lots more blood and therefore a lot more oxygen can be delivered to our working muscles. So it's our body's way of manipulating blood flow to get to more blood and more oxygen to our working muscles. So VO2. VO2 is simply oxygen consumption. Oxygen consumption is the volume of oxygen that is taken in through your respiratory system, transported via your cardiovascular system, and utilised by your muscular system for energy. So VO2, or oxygen consumption, the definition is the volume of oxygen that can be taken in, transported and utilised by the body for energy requirements. And there are many factors that influence your body's ability to take in, transport and utilise oxygen, and that's gender. Boys have a higher VO2 max than girls. Size, the bigger you are, the more oxygen you can consume, transport and utilise. Training, if you do aerobic training, your body becomes more efficient at taking in, transporting, and utilizing oxygen. Genetics is another one. About 50% of your genetic potential of your oxygen consumption comes from your parents. And finally, age. After you peak at around 25 years, your ability to take in, transport, and utilize oxygen declines with age.